Okay, let's put our new derivative rule for exponentials with a base not e into practice with a couple of examples here. And on number one, just remember you've got two ways to go with this. You either use the derivative rule that we just came up with, if you remember it, but if you don't, then you have to remember the definition, which will allow you to convert it to base e, and then take the definition. No. Take the derivative with that thing. Okay, either one, it doesn't matter. It will work. It'll give you the right answer. Okay, so let's first try it with our new derivative rule. So the derivative of 2 to the x, it's exponential, so it is always directly proportional to the original function. So that's 2 to the x. But then its constant of proportionality is the natural log of the base. I can write it just like that. This is how I usually think of it. I don't usually think of it in the reverse order like this. Usually think of it, oh, it's the exact same thing as the derivative that the function that we started with, and then we scale it by the natural log of the base. Okay, or you rewrite it as y is equal to, let's say, for example, I just can't remember what the derivative rule is. Okay, then for some reason you remember that 2 to the x is the same thing as e to the natural log of 2 times x, which is a composite function, so we take its derivative using the chain rule, and we get e to the natural log of 2 times x, because it's exponential, it's the same thing as what we started with, but then you multiply it times the natural log of, the derivative of the interior function. So the derivative of this is just the natural log of 2. Okay, and then one last thing is that you convert this thing back using the definition into 2 to the x. And you can see, yeah, we got the exact same thing. What'd you know? Okay, all right. On number 2, notice we do have a composite function here. We got 3x tucked inside of the 2 to the x function. So when I take its derivative, I have to use a chain rule. So the derivative of any exponential is that exponential. Okay. However, we need to scale it by the base, natural log of 2. And then also, this was a composite function. We have to multiply it times the derivative of that interior function, 3x. Derivative of 3x is just 3. So you know what? I'm just going to take that 3 right there. I'm just going to put it in front of this 3 natural log of 2. And for sure, you are absolutely done with this one. But what if this is multiple choice? You look for this answer. It's not there. Is there any kind of algebraic thing you can do with this? And there is. There's some stuff you can do with it. I'm going to leave this as it is for right now. But I'm going to use a property of exponents. I'm going to bring this 3 to the inside of this. So this would be the natural log of 2 raised to the third power. 2 to the third power is 8. Let's see, 2 to the 3x times the natural log of 8. You look down and it's still not one of the answer choices. Is there anything else you can do with it? There is, because this 2 to the third power can rearrange this as a power to a power, as in it's 2 to the third, all of that raised to the x. And then 2 to the third is 8 to the x. Okay, that's weird. It's weird because it's almost as if I took the derivative of 8 raised to the x. Because I did. It's just we didn't realize it. See what I just did right here? I rearranged this 2 to the 3x to 2 to the third raised to the x, which is the same thing as 8 to the x. So this function in disguise was 8 to the x, and you take its derivative, and it's 8 to the x. Same thing as what we started with. Multiply it by the natural log of that base. Okay, which means we are pretty much finally done with the chain rule lesson, where we were able to investigate, derive, and use this thing called the chain rule. And when do I use it? I use it whenever I'm taking the derivative of a composite function.